So when we talk about a particle moving along a line, generally we're going to talk about it like just moving along the x-axis probably, or just moving along the y-axis. Doesn't really matter, but just any line that it's moving along is going to be good enough. So we have a particle that's moving in a line. It might be moving sometimes to the right and then sometimes to the left, and it might be changing directions as many times as we want in between there. But it's just going to stay on that line. It's not going to, it's not going to go doing weird things like this, right? It's just staying in a line. First thing we want to find is what is the displacement of the particle in the first 2 seconds. So before we can even do that, we need to think about what is displacement? What does that mean?
The distance from the origin.
Right, or distance from, maybe from the origin, depending on where this particle started, but it's the distance from where it started to where it ended up during those first 2 seconds. So I might have started here, gone to here, and then came back to here, and then came back to here, right? The total distance I traveled was quite a bit, but my displacement is only this little bit, right? Everybody good on that being the displacement, but the total distance traveled would be, suppose this is 1 unit, it'd be 5, and then like 8, and then, 2 more units. Good or no?
Good.
Okay. So our displacement is the distance we are from our starting position. So we first have to figure out what our starting position is, which would be what value from this function?
3.
Right, which we got from s of 0, right? It's the position at t equals 0. So s of 0 is 3. And so we're starting at, suppose this is just like a number line. We're starting here at 3. And what's our position at 2 seconds?
-1.
-1, which means we're ending up here, which means we had a displacement of what?
-1.
No, because it's from where we started. We didn't start at the origin.
Oh, 4.
Started at 3, so we have a displacement of 4 meters. I think it said 4 meters. And if we wanted to clarify, it's 4 meters to the left of where we began, but you don't necessarily need to clarify that it's to the left or to the right. So we have a displacement of 4 meters to the left. All right, next thing is to find the average velocity of the particle during the first 4 seconds. So how do we find average velocity?
Distance over time.
Right, it's a change in the distance, so change in s in this case, divided by a change in time in the first 4 seconds. So real quickly, why don't you guys figure out the change in distance in those first 4 seconds and the change in time, and then I'll give you like a minute to do that, and we'll make sure you guys did it correctly. Ready, go. So our change in distance was what? It was s of 4 minus s of 0.
Yeah.
Which is what?
3 minus 3.
3 minus 3 over our 4 minus 0. Oops, that's 0 over 4, which gives us 0. So our average velocity was equal to 0 in the first 4 seconds because we started and we ended at the exact same place. Okay? So we started at 3 And after 4 seconds, we'd gone to the left some, clearly, because we ended up over at -1 for a while. And then we came back over to 3. So an average velocity, 0 meters per second. So now what we should be able to do is use a little bit of our calculus knowledge, though, to see what the instantaneous velocity of the particle is at t equals 4. And in order to find the actual velocity at an instant, we need to find a velocity function. And so how is the velocity function related to the position function?
It's its derivative.
It's its derivative. So v of t ought to be s prime of t. And what is s prime of t?
Two t minus 4.
2t minus 4. And if we want to figure out what that is, at t equals 4, we just plug it in, and what do we get? Should be 4 meters per second. So the instantaneous velocity at t equals 4 is 4 meters per second, whereas the average velocity in those first 4 seconds was 0. Good or no?
Good.
Okay. And what about if we wanted to find the acceleration of the particle at t equals 4? What does a of t equal?
The derivative of v of t.
Right, v prime, our derivative of v, which is just
Two.
2. And at t equals 4, what does 2 equal? It equals 2, right? So it doesn't matter. This particle has a constant acceleration, whether we were talking about at t equals 0, t equals 1, t equals 1,000. This particle has a constant acceleration of 2 meters per second squared. Okay. Everybody good with that?
Good.
All right. So if we were asked to describe the motion of the particle, first off, we know that it was traveling in which direction to begin with. To the left or to the right?
Left.
To the left, right? We should know that because we went from 3 to -1, but also we could take our velocity function, right? V of t was equal to 2t minus 4, right? And figure out when that particle stopped going left and when it started going right, and to see when that velocity function was positive or negative. And so the velocity would have been equal to 0 at t equals 2 seconds. And if we wanted to put that number on a number line and check, well, if we plug in a number less than 2 but greater than 0, something between 0 and 2, like 1, let's say, this comes out to be negative, doesn't it? Which tells us that we're moving to the left. But if we plug in a number greater than 2, like 3 or 1,000, we get a positive value, which tells us our particle is moving to the right. So if we were trying to describe the motion of the particle, we'd say, well, from t equals 0 to t equals 2, it's moving to the left at a constant acceleration of 2 meters per second squared. At t equals 2, it stops because it has a velocity that is 0, changes direction, and moves to the right for the rest of its domain. Good or no?
Good.
Cool. And that also answers this last part. When does the particle change direction? The particle can only change direction when its velocity is 0, right? It has to stop going left to start going right, or it has to stop going right to start going left. So it can only change directions when its velocity is 0, and that's what we found right here. Its velocity is 0 at t equals 2 seconds. Good or no?
Good.
All right. Let's see if we can figure this out. In fact, why don't you guys try and come up with the answer to the first one on your own, and then see if you can come up with a way to do the second one. And then after 2 or 3 minutes, I'll check in with you, and then we can get through it together if we need to. Sound good?
Yeah.
All right, I'll give you. Should be able to get the first one pretty quickly. The second one will take a little bit longer, so I'll give you 2 or 3 minutes for that. Ready, go. The velocity of the stone after 2 seconds, since we're given a height or a position function, right? Height is a position. All we need to do to find the velocity is figure out the velocity function. What's v of t? That'd be h prime of t, which is
10 minus t.
10 minus t. And if we want to figure out, v of 2, just be 10 minus 2, or 8 meters per second. So it's slowing down, right? As we throw it up, it started at a velocity of 10 meters per second, and it's slowing down due to gravity. Not much gravity, but a little bit of gravity on this planet. Good or no?
Good.
All right. So what about this one? The velocity of the stone after it has risen 25 meters. Well, how do we figure that out?
We found out what t,
Sorry, go ahead.
we find out what t is when the height is 25 meters.
Right, we got to figure out what t is when the height is 25. So our height is 25 equals 10t minus 1/2 t squared. And this is just a quadratic, right? Might not be great to have a 1/2 in front of the t squares we're trying to figure out, so it might be easier if we multiply everything by 2 and get 50 equals 20t minus t squared. And then we get t squared minus 20t plus 50 equals 0. And we should be able to solve that quadratic, right, to figure out at what t value is it at a height of 25 meters. I don't believe that factors nicely, so we'll need to use the quadratic formula. So that would be 20 plus or minus the square root of 400 minus 4 times 1 times 50, so 200, all over 2. So 20 plus or minus root 200 over 2. And what can we do with the plus or minus root 200? That can become 20 plus or minus 10 root 2 over 2. Or 10 plus or minus 5 root 2. Everybody agree with that?
Yes.
Yeah.
So which one is the time at which it has risen 25 meters? 10 plus 5 root 2 or 10 minus 5 root 2?
Plus 5 root 2, and 10 plus 5 root 2.
Okay, so let's figure out this real quick, right?
It's negative because the parabola is negative, right?
Right, this is a parabola that is opening down, so it's going to look like this. So this is the sort of the trajectory that this rock is going to go, or stone, right? It's going to go up and then come back down. And so the first t value, the smaller t value, should be when it has risen 25, and then the larger t value should be after it's hit the vertex here and then started to travel back down. It happens twice, right? And so the first one is at t equals 10 minus 5 root 2. And the second one is at 10 plus 5 root 2. Should be the same velocity. It shouldn't really matter. But we want to use 10 minus 5 root 2. So everybody good with why we're using the minus one instead of the plus one?
Yeah.
Okay. So now we just have 10 minus 5 root 2, which gives us what?
5√2.
5√2 meters per second. And if we'd done it the other way, we would have got negative 5√2 meters per second. So the 5√2 is indicating that it's still traveling up, and the negative 5√2 would be indicating that it's traveling down. A positive velocity means up, and a negative velocity means down. If we're going in the y direction, a positive velocity means right, and a negative velocity means left if we're going in the x direction. Everybody good?
Yeah.
All right. Okay, last thing that we want to do with these product and quotient rules, this is not related to the motion problems that we've been doing, but this is a super common multiple choice type question on the AP test, is they will give you a bunch of values of a function and its derivative at certain numbers, like at 2, let's say. And then they will say, what if we have a new function that is u times v, and we want to find the derivative of this one? Well, what's y prime equal to if y is u times v? Since this is one function times another, it ought to be the product.
Rule.
Right, the first function times the derivative of the second plus the second times the derivative of the first. Right? And so if we want to know what is y prime of 2, if y is u times v, it ought to just be u of 2, v prime of 2, plus v of 2, u prime of 2. What's u of 2? U of 2, they gave us, that's 3. V prime of 2, they gave us, that's 2. V of 2 is 1, and u prime of 2 is negative 4. So we end up with 6 minus 4, or 2. Good or no? Okay. And then if we were to do u over v, we'd just use
Quotient rule.
quotient rule. So that would be v times u prime minus u times v prime over v squared. And we'll plug in the values at 2 for each of those. So v of 2 was 1, u prime of 2 was negative 4, u of 2 was 3, and v prime of 2 is 2, all over v, which is 1 squared. And we'd end up with negative 4 minus 6 over 1, or negative 10. Those are pretty straightforward, but sometimes they confuse people on the AP test if they haven't seen them, just because it looks like a lot of weird numbers and stuff. Everybody good with that? Any questions or issues there?
No.
All right, cool. We are going to move on and learn how to take the derivatives of trig functions now. So give me 1 second to open up the new thing and we'll get started. All right, we want to find the derivative of f of x equals sine x. So how do we do that? Any thoughts on how we'll find that derivative? Okay, well, if you don't know how to find the derivative, the best thing to do is to set it up as a limit as h approaches 0 of the difference quotient. Yes, so that's f of x plus h. So what's f of x plus h? That's the sine of x plus h minus the sine of x all over h. If we can evaluate this limit and get something out of it, then that should be our derivative, right?
Yes.
Seems like that should be our derivative. So Well, plug into 0. What do we get? We get 0 over 0. Bummer. So we got to find something else to do with it. What should we do with this? What are some of the ways that we have dealt with these? Factoring, right? That's the first way. Anything you can factor out of there?
A sine.
So sine
Oh.
can't be factored out unless it's the exact same thing. So if I had a sine x plus 7 sine x, I could factor a sine x out of that. Or if I had, well, how about something rather than 7 sine x? Like if I had sine x plus x squared sine x, I could factor out a sine x. But I have different arguments on the sign, different things inside the parentheses on the sign. And so I can't.
Isn't there like something you can do to convert sine x plus h into something else, like with one of the kind of like trig functions?
Yes, there is a trig identity for the sine of
identity.
a plus b. It's not one that I asked you guys to memorize, but it's one in that those papers that I gave you said be familiar with these at least. So the formula for sine of x plus h is the sine of the first term, sine x, times the cosine of the second term, plus the cosine of the first term times the sine of the second term. Minus the sine x all over h. Hold on 1 second. All right, everybody good with that? That's in your trig packet. Sine x cosine h plus cosine x sine h. Hopefully you've seen that before. All right, cool. So now we've got a little bit more going on here. Now we've got some similar terms, and we no longer have a bunch of crap inside of the parentheses on that first sign. So what do we think we want to try and do here?
Split up the limit. One with just the cosine x and sine of h, and then one with sine of x cosine h minus sine of x.
Okay, so sine x cosine h minus sine x all over h, right? And then the other one with the cosine x sine h, you said?
Yeah.
And that's still got to be over h also because we're splitting them up with addition. Okay, cool. So now what?
You can factor out the sine of x and out in the one limit.
So sine x times cosine h minus 1 over h. I take the sine x out of that, and then this one is plus, what should I do with that one? Anything or no?
Leave it.
Just leave it for now, okay? So we could do that. Then I need to split it up a little bit in a second, but we can leave it for now. Well, what do we notice in both of those? Gonna give myself a little more room here. What do we notice in both of these ones down here at the bottom?
They're both over h.
Okay, they're both over h, right? And anything else that the over h part is important? Any limits that you already know just sitting around in there?
Sine of h over h.
Sine of h over h. We know that one is 1 if it was by itself, right? And what about on the other side?
Cosine of h minus 1 over h.
Right. This one is also equal to 0 if it was by itself. So couldn't I separate sine x times cosine h minus 1 over h as two different limits and separate this as cosine x times sine h over h? So I have four different limits. The limit as h approaches 0 sine x times the limit as h approaches 0 of cosine h minus 1 over h plus the limit as h approaches 0 of cosine x times the limit as h approaches 0 of sine h over h. Everybody agree with that? Should have written that smaller too. Still not going to have room to finish this. All right, what's the limit as h approaches 0 of sine x?
Sine x.
Sine x. And the limit as h approaches 0 of cosine h minus 1 over h?
0.
0. Plus, what's the limit as h approaches 0 of cosine x?
Cosine x.
Cosine x. And the limit as h approaches 0 of sine h is 1.
1.
No, sine h over h is 1. And so 0 times sine x is 0, and 1 times cosine x is cosine x. And so the derivative of the sine function is the cosine function. You're going to want to memorize the fact that the derivative of sine is cosine. I'm not going to ask you to repeat this process that we just did, but you do need to know the derivative of sine is cosine. So from this point right now forward, I'm going to assume that you have that memorized. Good?
Good.
All right. Could we find the derivative of cosine x?
Yes.
How do you think we would go about that?
The same process.
Same process. All right. So I don't think it's going to be helpful to us probably to go through and do this whole process. So I'm going to just sort of say what we would have to do here is find the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. And if you go through and do a very, very similar process, in fact, it's the same, except that the cosine of x plus h is not the same as the sine of x plus h. You end up getting negative sine of x. So the derivative of cosine is negative sine of x. I'm not going to make us go through the whole process, though. We just did it for sine, and it looks almost identical. Everybody okay with us calling the derivative of cosine negative sine? I promise you that's what it is.
Yeah.
All right. Cool. That's 2 trig functions. How many more do we have to go?
4.
4 more, at least that you guys know about, huh? All right. Finding the derivative of tangent x. Well, could we write this out as the limit as h approaches 0 of tangent of x plus h minus tangent of x all over h?
Yes.
For sure.
We definitely could. And then there's a rule for tangent of x plus h, right? Tangent x plus tangent h over 1 minus tangent x times tangent h. And then you'd have to get like a common denominator and it'd be a pain. But there should be an easier way to do this. If we want to find the derivative of tangent x, isn't there a way to rewrite that using some trig functions that we already know?
Since tan is sine over cosine, you can use the quotient rule.
Exactly. This is the derivative of sine x over cosine x, and that derivative should be able to be found using the quotient rule. So let's do that. So the derivative of a quotient is the denominator times the derivative of the numerator, which is
Cosine x.
cosine x, minus the numerator times the derivative of our denominator, which is another negative sine x, all over our
Denominator squared.
denominator squared, right? And this is u times v, right? This is u, this is dv minus v du, and this is the v squared down here. And what does that give us? That gives us cosine squared x plus sine squared x over cosine squared x. And what part of that can I simplify?
Cosine squared x plus sine squared x.
Equals what?
1.
Yep. So we got 1 over cosine squared x. And if I didn't want to write that as a fraction, what's 1 over cosine squared? Should be
Secant squared.
secant squared. The derivative of tangent x is secant squared x. You're going to want to memorize that one also. Okay, I'm going to give you guys a sheet with all of these on it, but you don't need to make your own or something. But you need to know the derivative of tangent is secant squared. Everybody okay with that? All right. What about the derivative of secant x? Is there a way to rewrite that using a trig function that we already know?
1 over cosine.
1 over cosine. And what rule would we use?
Quotient.
Quotient rule, or since this is just a constant over a function, we could use the reciprocal rule, which is just a simplified version of the quotient rule. So using the reciprocal rule, it always comes out to be negative, and then derivative of the denominator goes into the numerator. So what's the derivative of cosine?
Negative sine x.
Okay. And then in the denominator, we should end up with that thing squared, cosine squared. The negatives will cancel out, and we've got positive sine x over cosine squared x, which is a good answer, but not normally how we write this. Normally we write this as sine x over cosine x times 1 over cosine x, and then we turn this into a secant and this into a tangent. So normally we will say that the derivative of secant x is secant x times tangent x. Everybody good with that? Guess whether you should memorize that one or not.
Probably should.
Probably should. In fact, not just probably, you definitely should. The derivative of secant is secant x tangent x. You want to know that. All right, let's do another one. Cosecant x. That ought to be the derivative of 1 over sine x, which we should be able to use the reciprocal rule again. So negative derivative of the denominator over the denominator squared. Using the quotient rule, right? This becomes negative 1 over sine times cosine over sine, which gives us negative cosecant x cotangent x. Everybody okay with that? You should probably memorize. No, you should definitely memorize that one as well. Good or no?
Good.
Good.
All right. One more. Derivative of cotangent x. Anybody have a suggestion on how we want to go about that one?
The derivative of cosine over sine.
Okay. derivative of a quotient ought to be denominator times the derivative of the numerator, which is
Negative sin x.
minus the numerator times the derivative of the denominator over the denominator squared. Everybody good there?
Yeah.
Okay. What does that give us in the numerator? Negative sine squared minus cosine squared over sine squared. And how can I simplify that down?
The numerator would be 1.
Not quite, because it's got negative.
1.
So we got to factor out that negative, right? Which ought to give us a negative 1 in the numerator. And what's negative 1 over sine squared? That's negative cosecant squared x. Good or no?
Good.
Guess what? You should memorize that one. How else could we have done this derivative?
1 over tangent.
Yeah, we could have taken the derivative of 1 over tangent x. So that would have given us negative derivative of tangent, which we now know is secant squared, over tangent squared. We could have simplified that to, well, let's see, negative secant squared is fine. But if we took this tangent squared and took it out of the denominator, it would become a cotangent squared. And then I could write this as negative 1 over cosine squared times cosine squared over sine squared, which would give us negative 1 over sine squared, or negative cosecant squared x. So we would have got the same thing either way. Everybody good with that? Any questions on the derivatives of any of those trig functions? All right, here they all are, just right there in front of you if you want to take a picture of them so you have them for easy reference or something. But I will put up into, in fact, it's probably already up there in the other documents folder in the Google Drive, which has all of the derivatives you're going to need to have memorized, which includes a bunch more besides these ones and the regular rules that we already know. So you're going to want to get in there and take a look at that sooner rather than later. Everybody good so far?
Yeah.
All right, we're going to practice a few of these just using some of the other rules we know, like the quotient rule and the product rule, to help us find some derivatives of functions that we might not have been able to deal with before today. So if we want to find the derivative of tangent x over x, what do we need to use? Find f prime of x. We need to use the
Quotient rule.
quotient rule. All right, so quotient rule should still be saying v denominator, right, times derivative du of the numerator, which is
Secant squared x.
secant squared x, minus derivative of the denominator times the numerator. So the numerator is just tangent x, and the derivative of x is just 1 all over x squared. So all we got is x secant squared x minus tangent x over x squared. Good enough. Easy enough. Yeah. All right. What about this one? what should we do with secant x over sine x?
Use the quotient rule.
Use the quotient rule. Sine x times the derivative of secant, which is secant x tangent x, minus secant x times the derivative of sine x, which is cosine x, all over sine squared x. Can we simplify that down some? Should be able to. What's sine times secant? Secant is 1 over cosine, right?
Tangent.
So sine times secant ought to be tangent times another tangent ought to be tangent squared x. And then here, secant times cosine ought to just be
1.
1 all over sine squared x. Good or no?
Good.
All right. How about this one? Finding the derivative of secant squared x. Any thoughts on how we'll deal with that one?
Can we use the power rule?
So we cannot use the power rule. That's a great idea. And I'm going to say that we can't use the power rule because at this moment we can't, but at some point in the future we will sort of be able to use the power rule with this, probably tomorrow. But the power rule only works if you have x squared, like just a singular variable being squared. And secant x is not just a single variable, right? So we can't use the power rule for it until we learn some other tricks later on. Is there a way we can, oh, go ahead.
Can we separate it out and use the product rule?
Yeah, we could just write this as secant x, right? If we write it as secant x times secant x, then the derivative ought to be, well, first one, secant, times the derivative of secant, which is secant tangent, and then plus the other secant times the derivative of the other secant, which is also secant x tangent x, which gives us 2 secant squared x tangent x. Good or no? All right. Let's do this one. This will be fun. Finding the first 4 derivatives of sine x. So what's the first derivative? We know that one already, right? Derivative of sine is
Cosine x.
cosine x. What's the derivative of cosine? We should know that one. That's our second derivative.
Negative sign.
Negative sine. What's our third derivative?
Negative cosine.
Negative cosine, right? That negative is just a constant out in front, so just take the derivative of sine and apply the negative. And what about the fourth derivative?
Sine.
Should go right back to sine, right? And we'll notice that we know that, sine is a cyclical function, right? Sine repeats itself. Well, even the derivatives of sine repeat themselves. Every 4 derivatives, you end up back with the same function. So if this was my position function, right, then this would be my velocity and my acceleration, right? And then my jerk, and then my jounce. So the jounce or the snap is the same as the actual function was if we started with the sine x function. Everybody good with that? We note that if I asked you what's the 100th derivative of sine, since 100 is a multiple of 4, then the derivative of the 100th derivative of sine ought to be
Sine.
sine. Right? If I asked you what's the 101st derivative of sine, it should be
Cosine.
cosine. Cool. All right. This will be a good one. Let's find the second derivative of secant x. So the first derivative is
Secant x tangent x.
secant x tangent x, right? We got that memorized now. So the second derivative will have to use the
Product rule.
product rule. So that'll be secant x times the derivative of tangent, which is derivative of tangent is secant squared plus tangent times the derivative of secant, which is secant x tangent x. Everybody good there? Secant cubed plus secant x tangent squared x. If you wanted to factor a secant out, you could, but there's no necessary reason for that. Good or no?
Good.
Okay, let's see if we can find the equation of the normal line to tangent x at the point pi over 4, 1. So how do we find the equation of a normal line? Or what is a normal line? Do you remember what a normal line is?
The negative reciprocal of the tangent line.
Right, it should have a slope that's the opposite reciprocal of the tangent line slope. And we find the tangent slope, or the tangent line's slope, by using a how do we find the slope of the tangent line to a function? We take a
Derivative.
derivative. So y prime ought to be secant squared x. And if we want to figure out what that is at pi over 4, that would be secant squared of pi over 4. And what's the secant of pi over 4? This is the part where you immediately unmute yourself and tell me the right answer, because you know all of the trig functions and all of those important values, all those unit circle values. Maybe this will help. What's the cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. So this is 1 over root 2 over 2 squared. Root 2 over 2 squared is 1 over 2/4, right? Which gives us 4/2 or 2. So the slope of the tangent line is 2, which tells us that the slope of the normal line is
-2.
negative, not negative 2, opposite reciprocal, so negative.
Half.
And so our equation ought to be y minus 1, using point slope form, right? Y minus y1 equals m times x minus x1. Good or no?
Good.
And if we wanted to put this in Desmos, we could take a look at it. So here's tangent x. And we had y minus 1 equals negative 1/2 times x minus pi over 4. And at this point, pi over 4, 1, it sure looks like that is perpendicular to it, doesn't it? At this particular point. And we could even, well, we could look in and see the tangent line would have been y minus 1 equals 2 times x minus pi over 4, right? And sure does look like that's tangent to that pi over 4 comma 1 point right there, doesn't it? And those are definitely perpendicular. Good or no?
Good.
All right. Let's find another derivative of cotangent plus cosecant times tangent minus sine. How should we go about this? There's two options, right? This is a function times another function, right? So I could use the product rule, or I could simplify it down first. So who wants to try to simplify this by distributing first, and who wants to just use the product rule? Anybody have an opinion on that?
Distribution.
Distribute first, yeah. So I'm gonna say this always, unless you already see the derivative and it's really easy to find, always simplify trig first. Okay. If there's any trig to simplify first, do it. So we got f of x is equal to cotangent times tangent. What's cotangent times tangent?
1.
1. And then cotangent times negative sine. Well, that's cosine over sine times negative sine. What should that be?
-1 times cosine.
Okay, negative cosine. And what about cosecant times tangent? That's 1 over sine times sine over cosine. So that ought to just be 1 over cosine, which is secant. And then lastly, cosecant times negative sine ought to be
-1.
-1. So really f of x is equal to secant x minus cosine x. And what's the derivative of secant x?
Secant x tangent x.
Secant x tangent x. And the derivative of negative cosine ought to be
Sine.
sine x. And there's our answer. And that was a lot easier than trying to do the product rule for sure. Because the product rule, you'd have had a derivative of cotangent and a derivative of cosecant times tangent minus sine, and then the cotangent plus cosecant times the derivative of tangent minus sine, and it would have been a way bigger mess to distribute. So try to distribute first, simplify the trig first, and see what you get. Everybody good there or no? All right. Why don't you guys see if you can find this derivative on your own, and then we'll go through it in about 2 or 3 minutes. Use your trig derivatives and use the quotient rule. Ready, go.
Yeah.
All right, here we go. So f prime of x ought to equal 1 plus cosine times the derivative of sine, which is
Cosine.
Cosine minus the sine times the derivative of 1 plus cosine, which is negative sine, all over 1 plus cosine x squared. And hopefully you try to simplify this down a little bit. What do we end up with if we do that? Should get cosine x, if you distribute that, plus cosine squared x, plus a sine squared x, all over 1 plus cosine x squared. And that gives us what? 1 plus cosine x in the numerator, if we simplify the cosine squared plus the sine squared, over 1 plus cosine x squared. And what does that simplify to? Just 1 over 1 plus cosine x. Is that what you all got?
Yeah.
All right. Any questions or issues there? All right. Let's see. I don't think we need to bother with that. That's not too exciting of a problem. I think we're good. I think we'll stop right there.